Yeah.
Okay. So welcome everyone to the 2024 Turing Award winner speaker series at the Georgia Institute of Technology, College Computing. This event is sponsored by AI2 Incubator. Uh, During the course of the semester, 5 Turing Award winners, 1 Nobel laureate in physics, and many other famous computer scientists will be speaking and giving presentations to 1,000 plus RSVP students and faculty from the top computer science universities in the world. So thank you very much to our esteemed speakers, series advisors, Dr. Svi Galil and Dr. Bjarne Sestrat for helping to make this initiative a reality. I'm so grateful for your advice and guidance as we planned this tremendous speaker series. And then thank you as well to our favorite LinkedIn influencer and sponsor, Aish Saravazian, for her assistance with helping market the series to her 485,000 plus LinkedIn followers. We simply could not have achieved our stellar attendance numbers without you. Most importantly, for our thank you, the biggest thank you today, Dr. Leslie Lamport, for agreeing to speak with us. We really, really appreciate your willingness to take the time. Uh, and so I'm extremely excited to announce our speaker, the insanely accomplished computer scientist and the winner of the 2013 Turing Award for imposing clear, well-defined coherence on the seemingly chaotic behavior of distributed systems, Dr. Leslie Lamport. Dr. Lamport received the Turing Award for fundamental contributions to the theory and practice of distributed and concurrent systems, notably the invention of concepts such as causality and logical clocks, safety and liveness, replicated state machines, and sequential consistency. That is at least according to Wikipedia. Dr. Lamport is best known for his seminal work, strongly influencing later work in distributed systems, and as the initial developer of the document preparation system LaTeX. Hopefully, I'm pronouncing that correctly, and the author of its first manual. Dr. Lamport's research contributions have laid the foundations of the theory of distributed systems, and among his most notable papers are time, clocks, and ordering of events in a distributed system, how to make a multiprocessor computer that correctly executes multiprocess programs, the Byzantine generals problem, distributed snapshots determining global states of a distributed system, and the part-time parliament. These papers relate to such concepts as logical clocks and Byzantine failures. His papers are among the most cited papers in the field of computer science and describe algorithms to solve many fundamental problems in distributed systems, including Paxos, Paxos algorithm for consensus, the Bakery algorithm for mutual exclusion of multiple threads in a computer system that requires the same resources at the same time, the Chanley-Lamport algorithm for the determination of consistent global states, and the Lamport signature, one of the prototypes of the digital signature. Dr. Lamport is also known for his work on temporal logic, where he introduced the temporal logic of actions, TLA. TLA is used to describe behaviors of concurrent and distributed systems. Among Dr. Lamport's most recent contributions uh, is TLA Plus, a language for specifying and reasoning about concurrent and reactive systems. Dr. Lamport has also won many of the most prestigious computer science awards, and here are just a few. The the Dijkstra Prize, I'm pronouncing that right. Um, the Emmanuel R. Peoria Award, the IEEE, Emmanuel E. Peoria Award, the IEEE John von Neumann Medal, the Turing Award, member of the National Academy of Sciences, and ACM Fellow. Now let's take it into a Q&A mode. As we strongly stipulated and required on our SB invite, students are required to watch Dr. Lamport's How to Write a 21st Century Proof presentation prior to this Q&A session. And now I encourage uh, anyone with questions, you can raise your virtual hand, and then we will also be going through a list of 30 questions that we have compiled per your recommendations, and we'll do our best to answer all of your questions. So thank you very much, and everyone, let's give a warm introduction for Dr. Leslie Lamport.
Thank you.
Of course.
All right, so
okay,
we have a document prepared here with about 30 questions that folks have sent us. Again, Dr. Leslie Lamport, thank you for joining us and taking part in this speaker series. We are very appreciative. The format that we were thinking of proceeding with is that I go ahead and ask these questions one by one. We have a document prepared that I'm happy to share with you also so that you can read them.
Okay. You said I can read.
Yeah, and better, I can also share the screen so that everybody can see the questions at the same time.
Okay, yeah, that would probably be a good idea so I could see them.
Yep, absolutely.
Thanks, Parsa.
Of course. All right, is everyone able to see the screen here?
Okay.
And zoom in just a bit too.
Oh, yeah, that's much better. Thank you.
Of course, no problem.
Okay, sometimes an equation and a proof can be written requiring a subtle interpretation when authors attempt to be brief. Well, I'm not sure what subtle interpretation is, but I suspect if something that you write requires subtle interpretation, it means it hasn't been written precisely or clearly. And so proof is quite likely to be an error. You shouldn't be writing subtle things that require interpretations when you're writing proofs.
Parsa, do you want to read these aloud as well so that
yeah, I'll go ahead and read these aloud. So any advice generally for students who have just learned proofs?
Well, I'm actually curious as to how they learn proofs. I mean, be hard for them to learn proofs from mathematicians who, well, I mean, I shouldn't say that mathematicians, don't write good proofs because mathematicians write proofs for different reasons than computer scientists do. Computer scientists are, well, programming computers requires a great deal of rigor and precision. And, very tiny errors can just cause a system to crash. And so they have to make sure that they've gotten things right. And if you've learned proofs from mathematicians, you haven't learned how to write proofs that are good at catching that kind of error. They're not good at catching, they're not good at catching the kinds of errors, that mathematicians are supposed to care about. As I think I may have mentioned in that paper, I have some statistics from 75 non-randomly chosen papers that suggest that, but not cherry-picked, just not picked to be ones likely to have errors, but just I won't go into how I got those, the pieces of data, but 1/3 of them contained incorrect results. But mathematicians don't care that much about it because if something is interesting, really important, enough people will read it that they'll, probably catch those errors, and so it doesn't matter. But if you're going to write a proof of correctness of a program or an algorithm, if it's your program, nobody else is going to read it. So you better make sure you have it right. And a good way to learn proofs, is to learn to write proofs that a theorem prover will accept. Now, the TLA plus theorem prover it's not the best one for somebody to learn to write proofs with. It's not what it was designed for, but it does support hierarchically structured proofs. And so if you can't find something better around, then try that. But the idea is you have to have a sense of what a rigorous proof is, so that you don't write a completely rigorous proof in order to convince the theorem prover most of the time. But you should understand that the proofs that you write could in principle be made sufficiently rigorous that with a lot of work you could write them to be checked by a theorem prover. And a very good way to learn what rigorous enough means is to use a theorem prover and learn what you have to do to convince it that what you're proving is true.
Do the way that mathematicians and computer scientists do they approach proofs very differently in terms of how each discipline creates a proof, if that makes sense?
Well, first of all, computer scientists, they're sort of, you can put them into two categories, actually computer scientists and computer engineers. People who are writing proofs of theorems and people who are writing proofs of correctness of algorithms or programs. And so, they're very different. People who are, people who write correctness of algorithms actually really generally work like mathematicians writing proofs of correctness of theorems. They don't write them very carefully or very rigorously. And especially with concurrent algorithms, that can easily lead to errors. The people who write proofs of programs, they're generally have realized that the only way they're really going to get the necessary degree of correctness of those is by writing them for a theorem prover to check.
Okay. Thank you.
All right. So, next question. Will the way of writing proofs change in the generative AI era? And if so, how?
Well, the way, some things like Chat GPT goes, you shouldn't trust anything that they say, especially if they're trying to write a proof. No reason to believe that anything they say is actually true. Now, my hope is that, writing proofs at the detail to convince theorem provers is hard work. And I think in principle, AI can be used to help someone write those proofs. In other words, to take what someone is trying to prove, the precise statement of it, and actually figure out how to construct the necessary instructions for a theorem prover to prove that theorem.
Kind of like is it like a co-pilot, like kind of assisting writing?
Yeah, I'm not sure. Possibly really be used in the theorem prover itself, so that the theorem prover itself would just become smarter because it's using AI and not just decision procedures. So it might become human beings have some way of proving things that is a lot more efficient than decision procedures, which in principle have very high complexity. So I think, well, the way you write a proof, at least with a hierarchically structured proof with a theorem prover, is you write something and you ask the theorem prover, well, is this true? And the theorem prover says, I don't know, I can't figure it out. So you break it into steps, And then you ask, are all these steps true? And the theorem prover says, well, I can prove steps 1, 2, and 4, but I can't prove step 3. And then you say, okay, then you break up step 3. And very often what happens is you discover that, at least with our prover, that when you get down to about 3 levels, you realize that you forgot to tell it to use one fact that it needed. And then when you start, you can go up and give it that fact a couple of levels higher, and it will then prove it. But I think that's somewhat unique to our theorem prover, well, although I'm not sure. But at any rate, basically, how does a human being figure out how to decompose the proof? Well, some of that decomposition can be done automatically based on simply the structure of the theorem. In other words, if the theorem says you're supposed to prove A, B, and C, then you break it into 3 steps, proving A, B, proving C. The other way, if you have a formula which says, A or B or C implies something, well, you prove that A implies it, B implies it, and C implies it. And that'll generally take you about, proving the correctness of a program or an algorithm about, 3 levels deep without thinking. And then you have to use intelligence. Well, and intelligence is something that, AI is supposed to be trying to, simulate or help with. So that will help figure out, if you can't figure, if the theorem prover can't prove something, well, how do you break it up into steps to that it can prove?
Are you against the idea of? I would assume that, and feel free to correct me if I'm incorrect. AI as like a supplement to the human brain in terms of proofwriting. Is that? I'm kind of curious. Where do you stand in terms of AI's role in proofwriting?
Well, AI's use in proofwriting should be inside a theorem prover. And I'm not a builder of theorem provers. The theorem provers for TLA plus, no one worked well. Only one of them was actually the TLA plus actually uses multiple back-end theorem provers, and you can tell it which back-end theorem prover to use, and you learn, which theorem provers are good at which kind of thing. But I don't know anything about building those theorem provers, so I can't tell you how best to use AI on that. The thing you don't want to do is just sort of ask Chat GPT, well, is this program correct?
Right. There's no way to verify that, we don't know that it knows anything.
And generally, if you build, theorem provers use heuristics, but the actual proof engine will check that, isn't based on heuristics. It's sort of the heuristics are used to decompose the problem, but once you've decomposed it, you have a program that does not depend on intelligence in some sense. It depends on algorithms to check those smaller pieces.
Cool.
And those algorithms have to be provably correct.
Right. Parsa, do you want to suggest the next question?
Yeah. So how do you see proofs in the 21st century in terms of computer AI assisted proofs, which I guess we just went over, completely automatic proof systems, and then making proofs generally and the problems in the first place more searchable as a way of better collaboration and communication among scientists? Specifically,
let's also make sure that the questions aren't redundant. If we have redundancy, let's make sure that we.
Yep.
Yeah. Okay. Well, I think I answered 1 and 2 pretty much, because
Yeah.
Yep.
I don't know
Yep.
what completely well, I mean, the goal is to make something that's completely automatic. You can just give it the theorem prover a theorem and say go to it. But in some sense, no matter how good your theorem prover is, you're going to want to prove things that are too hard for it to prove, and you're going to have to break it down. And so the real question is, what you're trying to do is make proof systems that you don't have to break down as far as you now do. And as far as searching, you know, well, the proofs shouldn't be searchable in some sense. That the results are, and that's not a problem of theorem proving or how you prove a theorem. It's a problem of how you look up theorems, and that don't have anything to say about that.
All right. Moving on. So there are 17th century proofs, 21st century proofs, and mechanized proofs, each more robust than the previous. Should we be mechanizing all proofs? If not, why? And if the reason is about the time it consumes to mechanize a proof, then why not use the same argument to prefer 17th century over the 21st century proofs?
Well, if you're not using something, if you're writing equations and you're not using some program to manipulate the equations, why write them with symbols instead of in words? Why write to plus sign 4? Why not write the sum of 2 and 4? Well, for the simple reason that it makes it harder to read. And
it's more efficient, right? Like it's a more effective way to communicate.
Yeah. And the reason for writing, my style of 21st, what I think 21st century proof should be like, is that they're easier to read and understand.
Is it just that people are lazy and they don't want to adapt to current times, or are there certain reasons that?
Oh yeah, I mean, the incentives are all wrong for writing rigorous proofs, because if somebody writes a paragraph style proof, that he believes, well, the referees are going to believe it too. So what's the incentive for him to write a more rigorous proof? The best case, he'll discover that his theorem is correct, which is something he believed in the first place. And the worst case is he will learn that it's not correct and he doesn't get the publication. So, the incentives are all wrong. Mathematicians seem to be really afraid that they will have to write machine check proofs. Whenever I show how to write this proof, this proof method, even though I say very clearly, you can write the statements in the proof at whatever level of formality you want. You just structure them so that it's easy to understand what you're doing. And the response that I get when I do this is very often, I don't want to write proofs for a computer to check. So I think what that indicates is that there's some sort of very deep insecurity among mathematicians that they're going to have to write proofs that are rigorous enough to convince a computer, and that frightens them. But I'm not a psychologist. I'm not going to try to psychoanalyze mathematicians. I can just report that the objections that I get to writing structured proofs tend to be very irrational. And when people act irrationally, fear seems to be a common reason for people to act irrationally. That's all I can say about it.
Do you think this could be solved by like better training in terms of like how mathematicians are trained in like PhD programs to uh, change these insecurities that they feel, or we think that just mathematicians are an insecure bunch and like
Well,
I guess
people are not going to teach, something that they don't want to do themselves.
right.
So the idea is that, there are mathematicians, most mathematicians are basically, they want to prove theorems and get them published. But there are mathematicians who are interested in teaching. And, uh, I have a small hope that they will realize that structuring proofs makes them easier to understand, and that they might start adopting them. But uh, mathematicians are very conservative, so I've pretty
Right.
much given up trying to convince them to write structured proofs. But
Are
computer
there any small
scientists who should be interested, in the programs that they write being correct, or the algorithms that they write, maybe there's some hope of convincing them to write more rigorous proofs.
Are there any like small organizations that are dedicated towards trying to foster that? Maybe if it's not like
No, there are a small number of people like me who are interested in it, and they generally each have their own way of doing it. Uh,
hmm,
I'm I don't know anyone actually uh, who not only talks about how to write proofs, but actually uses them in publishing proofs of interesting results.
hmm,
Of results that they're interested. I frankly can't think of anyone who does it. I guess
hmm,
Dijkstra tried. Yeah, Dijkstra did it.
hmm,
He wasn't interested in being as
hmm.
yeah. I guess he didn't. Yeah. Well,
Maybe
I shouldn't try
is
to
it maybe
characterize what he did.
is it maybe like the divergence between wanting to publish for the sake of being a top publisher versus like an actual passion for the mathematics and the work?
Yeah.
Is that
Yeah. Well, I'd say that Dijkstra did have a passion uh, for trying to make things easy to understand, I would say,
hmm,
and rigorous. So uh, and he yeah, I mean
right?
he had the right attitude. We had different ideas about how proofs should be written, uh,
Hmm.
coming from different backgrounds. But
Right.
uh, the I respect what he did,
Yeah.
and certainly the way he tried to write proofs. Uh, I think uh, he was very, what's the word, honest, I would say, and you know really trying to do things correctly.
Hmm. Parsa, do you want
Yep. We
to?
can move on to the next question. Luciano asks, have you thought of applying an analogous procedure for outlining the entire reasoning behind a CS paper, even when there aren't any formal proofs? It seems to me that if one follows the scientific method correctly, having a summary of all the steps taken to reach their conclusions, even when purely empirical, could greatly increase the clarity of a paper.
Uh, well, I don't know exactly what an analogous procedure would be. One thing I have found, for example, is that structuring things in terms of lists and even and sublists is often a good way to make things easier to understand. And I do that, I think, more than most writers. But well, yeah, and when structures a paper into sections, subsections, subsections, you don't write a paper, just one whole series of paragraphs. So yeah, everybody structures their papers. Perhaps I try to structure a little bit more deeply than other people. The other hand,
Yes.
Chris Newcomb, who's the engineer at Amazon who introduced Amazon to TLA Plus, and who's now at Oracle. He has said that he has used the principles of structured proofs in ways that I've never thought of, like in structuring arguments, or for making a decision. To structure the arguments, pro
Like
and
a
con, and
purchasing decision, like an Amazon.
yeah, something. Well, I'm not purchasing, but in particular, but things that that where what you're doing does not have a formal mathematical answer, uh, but sort of more everyday things. And I've asked him, I suggested that I would really love to and other people would, to find out how, what that means, and how, for, with examples, to write something, but he's too busy to do any writing. So I don't know how he does it.
Parsa, do you want to ask the next question?
Yep. So what are your thoughts about taking mathematical proofs one step further and having each component of the proof come with code that others can run to verify the truth of that component? In many ways, this modern approach to writing proofs resembles unit testing of code, so perhaps unit testing principles can be applied to proofs.
Well, that's what you have when you write a TLA, proof for the TLA plus theorem prover. The fundamental step, the paragraph style proof at the at the lowest level of a structured proof, of an informal structured proof, is basically replaced by instructions to the theorem prover. Those instructions for the TLA plus prover are mostly what statements to use, and also what back-end theorem prover to use. But that's what's done.
Parsa, do you want to?
Yeah, and Gary asks as a follow-up, is there any project or effort underway to create structured proofs of major results, such as Wow's proof of Fermat's or Perelman's proof of the Poincare conjecture, both as an alternative verification, but also possibly as educational?
Well, there are people who create, who try to write mechanical proofs of them, and so if you basically can't write a proof of something like, well, look, Georges Gantier, the first sort of major result like that proved mechanically was Georges Gantier's proof of the four-color theorem. And he used coq. Now, coq does not have into its language. It's a you know, I regard, not one of the back-end theorem provers we use, but it's, what I would regard as a back-end theorem prover. But
Mhm.
the Coq input language does not have this kind of structure in the proofs. So I asked George, well, how could he possibly have proved something so complicated as the four-color theorem without, having a structured proof? And he said, of course he used the structured proof. He was actually using some system that was built on top of Coq that would provide, that kind of structuring. So however you write that proof, if that's something like that, it has to be structured. You just lose your mind if you just try to write an unstructured proof is just a series of steps. And so, because unstructured proofs of, the four-color theorem would be a series of, 20,000 steps or something. Nobody can write or read a proof like that. You have to structure something. And really, the question is, what kind of support you have to do that structuring. Do you have to do the structuring, on paper in your head and, mathematicians have a structure, a one-level structure in some sense of lemmas. You prove a theorem and it's based on lemmas. But when those lemmas are proved on other lemmas and those other lemmas are based on other lemmas, how do you keep track of it? Well, the way mathematicians now work, they have to keep track of it in their heads, or some way on paper. And so the question of what kind of support they have.
Does when it comes to proofs, in terms of this problem of people not following writing the most rigorous proofs, this applies to industry as well? Do we have a lot of issues in industry in terms of, like some of these big high tech companies? Do they use proofs at all in terms of their work?
Well, I don't know what goes on in other aspects of engineering, but very few people, who build computer systems write any kind of proof. And in fact, I will agree with that in some sense. For most of the things that are done, they're not now cost effective.
Okay.
But that's why, there are tools for checking TLA plus specifications of programs besides the theorem prover, namely, there's a model checker. And that gives you a lot more bang for your buck in terms of the cost of finding errors. And so, currently, proofs, and also if you want the kind of if the program you're writing is sufficiently critical that you need proofs, then it'll be critical enough that you're not going to be satisfied with hand proofs, and so you'll need machine checked proofs. So, which is sort of, in some sense, it's orthogonal to what I'm doing. What I'm trying to do is get the idea of structuring to be carried down to the levels where it's now done in paragraphs. You don't structure a proof, no matter how you're going to try to do it. You're not going to structure a proof of the four-color theorem by just a series of paragraphs. You're going to be structuring the lemmas you use. But then at the lemmas themselves, there'll be, paragraph proofs. And I'm saying, let's make those, let's carry that structuring down, and, down to the level of the lemmas as well. Because it's just as good an idea there.
Okay. Prashant asks, how is quantum computing going to affect the proof of work algorithms?
Well, they are talking about two things that I know nothing about, or quantum computing and proof of work algorithms.
Okay.
Okay.
We can move on.
Parsa, do you want to go to the next question?
Yep. So this feels a bit repetitive.
Yeah,
But
then
I
if
guess we
it's
can-
repetitive, you can skip it.
Yeah.
Yeah.
So this is a bit interesting. Do you have any thoughts about how theorem provers can change the social process of proof?
Yeah.
proofs?
Well, I haven't seen sign of working mathematicians using theorem provers for research. I know some cases where mathematicians will use computers to check a conjecture by looking for counterexample, but I don't know mathematicians who use theorem provers as they're part of their daily work of with writing theorems. So what I'm as I said in the past, AI may make theorem provers smart enough that more mathematicians will do that. That's my hope, but I'm afraid that the economic incentive
Mhm.
for doing that is may not be good enough for that to happen, because
Right.
basically you can't make as much money by
Yeah.
proving theorems as you can by driving cars.
All right. Claudia asks, given the availability of automated reasoning tools, are there particular strategies or considerations you find crucial when leveraging these tools to enhance the rigor and efficiency of proof construction?
Now, this is down at the level of building proof checkers, and that's not what I know anything about.
All right.
Parsa can just go next.
What would you consider as the most important open problem about structured proofs?
Getting people to use them. I mean, I don't know, what's the most important problem of writing a paper? Uh, that's well, okay. Actually, maybe there is I wouldn't call it a problem about structured proofs, but basically writing papers on the remains of dead trees. Uh, you know, we should be reading proofs and reading other things, on a computer, so we can use things that you can't do with, uh, pieces of paper. Like just click on something, see a word and just click on it and get its definition. Well, what you want for reading structured proofs is a kind of hypertext reader, where you can uh, basically hide the parts that you're not interested in and just see what you're interested in front of you, and understand the structure. To when you write a structured proof on paper, the only way I know of indicating the structure is with indentation. Step The proof of step 1 has steps 1.1 and 1.2 that are indented, and then 1.2.3 is indented further, and at some point you run out of paper. But with structured proofs, you can go on forever and still keep track of things. And with structured text readers, now you can do that with there's when you use the theorem prover, you can use our front end for it, which provides that kind of structuring and that kind of, being able to read the hypertext in a way by, just display, step 1.2.3 without, all of the other things that are, you open that proof without having to have the rest of the stuff opened. It still winds up indented, but it you don't have all that other clutter of all the other stuff. You just actually can just see the statements that you could use.
Mhm.
And so that makes it a lot easier to read the proof. The people who were building, things like the web, uh,
Mhm.
they, that kind of structuring is not built into HTML.
Hmm.
In order to do it on a web page, you have to do JavaScript programming
Hmm.
to get it to work. So, and I don't know of any systems that are, layered on top of HTML for even doing that. So,
Hmm.
uh, so that's, I would suppose you would say, is an open problem. Getting systems so that you can write your proof and read it, a structured proof, and read it the way it should be read.
Right.
Now, for the sake of time, as we approach these last 13 minutes and being mindful, I'll allow you to choose which questions, because we're only about halfway or a third of the way through these, and I want to make sure you're entertaining the ones you're most
We also want to
interested
be
in.
very cognizant of your time, Dr. Lamport. If you need to leave for any reason, we want to make sure that we're not taking up too much of your time.
Yeah, okay. I'm not under any very strict time constraints.
Okay. I'm going to make sure.
Oh, intricacies when writing structured proofs for algorithms and protocols. The intricacies are in the algorithms and the protocols, not in this, not in writing the structured proofs. What about programming languages fit in the context of 21st century proofs? Well, another thing I do uh, is that well, one of my mantras is coding is not programming, and what you call
Hmm.
programming languages I like to call coding languages. And
Hmm.
because programming, there's another part of programming that you should do before you write any code, which is figuring out what the program is supposed to do and figuring out how it should do it. Another way of another way of looking at it is that, a code may use an algorithm, but an
Mhm.
algorithm is something at a higher level than the code. The
Mhm.
code implements an algorithm, and you
Mhm.
shouldn't use a coding language for describing an algorithm. Uh, that's why I invented the language TLA plus. That's a language, that you write at a higher level, and I think uh, proofs, uh, if they're to be used, are most cost effective at that higher level. So they're more cost effective in some sense, reasoning about uh, not about the code
Mhm.
written in languages like Lean. I don't know what Lean is like,
Mhm.
but in the languages that you uh, write the things you should be, reasoning about uh,
Mhm.
at a level before you write code.
So if you get the algorithm more rigorous, you're going to be more cost effective in terms of.
Well, no, the thing is that the reason is that algorithm errors, especially concurrent algorithm errors, are
Mhm.
very hard to detect at the
Mhm.
code level, and you're hard to correct at the code level. So it's much more
Mhm.
cost effective to catch those errors at the algorithm level,
Right.
and that's what's, cost effective. Uh, okay, so this is an example of important compilers. I don't know nothing about the CompCert C. So, do you think late 21st, we should have talked about that? How can proof existence there be? Actually, Coq, to my knowledge, is not based on structured proofs. I haven't used Isabel. You know, yeah, well, as I said, you need to structure evidence proof before, before you can throw it at a theorem prover. That's something like Coq. And the, best you can hope for is that, with theorem provers, or what they're called theorem provers, but they're really, I like to call them proof checkers, is that you can have them check higher level proofs. Okay, for improving precise and rigorous. What about legibility? Shouldn't proofs? Well, that's what I said. Structured proofs are easier to read. One thing that they would be much easier to read if you were reading them in hypertext. But they are easier to read. It takes a little bit to get used to it, but if you want to be precise and rigorous, you pretty much need to be legible, because you need to understand what your proof in order to make sure that it's correct. Are you concerned about? Well, no, I'm not concerned. Lean. It's called a proof assistant. I don't know if it's a programming language or a proof assistant, so I can't answer that. See a common library or substeps in a proof. Well, probably with a common library is that it's being built for theorem provers, and theorem provers have their own different input languages. So that's the issue, and whether people will be convinced on, a common language for writing mathematics. I'm not optimistic about that, but interest in form. What is the best place to start? Interested in formal methods. I don't know. It's how they're taught at the universities these days, so I can't comment on that. Can somebody go down on the questions?
Yeah.
Was most of them in the traditional mathematical proofs? It's a different differences. They make more sense. Make more sense than writing things in prose. You agree with? Right. Let's see. If you examine the degree, affect the ability to pick up on TLA plus and put it to use. Actually, the one thing that I've found about programming language is that when you write specifications, you tend to need to be able to define, write recursive definitions of functions. And what I found is that people who have programmed in a what's it called, a functional programming language, understand recursion much better than the people who have programmed only in imperative languages. That's the only difference I can say.
Do you know why that is, or it's just like is the
because basically what you write a proof in what you write as a loop in an imperative language, you write as a recursion in a functional language. So, okay, what do you think, perhaps? I'm not going to predict what's going to happen in the 22nd century. Its own unique way for development. Every branch has its own unique way for they do. I haven't seen any branch of mathematics talk about structured proofs. No, there's nothing. Branches of mathematics don't have their own, invent their own ways of writing proofs. They use the standard mathematicians way, which nowadays is paragraphs, and they can just easily now use structured proofs. When did computer scientists become a group of people? Well, I guess all I know is when computer scientists, came into being, and that seems to have happened in around the 70s. When you could start majoring in computer science at a university. Okay, what are the biggest that would prevent wide adoption of modern scientific and academic communities? I think I've talked about what prevents its adoption in mathematics. I don't know about other communities. And your most traveling problem you face as a computer scientist? Oh, I don't want to go into what motivated me as a computer scientist and all that. Not relevant.
Next.
What is your view on the? I think that sort of discussed the top one here.
Right.
And should math students learn to use them? Yeah, I think it would be good, because they would for them to learn to understand what a formal proof is. So they will know in some sense in some sense, in reality, formal proofs are a Platonic ideal that one strives for, but can't get close to. But I think to understand, it helps to understand what that Platonic ideal is. Okay.
Right.
You mentioned, what do you recommend to make it easy as possible? Write better proof checkers. Well, actually, I've just said there are technical tools that can do it for you, like doing when you can decompose a proof system for a proof of a statement based on the logical structure of the statement. Then there's the TLA plus prover has a tool that has a feature that will let you do that. Automatically decompose the proof of A and B and C into the proof of A and the proof of B and the proof of C. But little stuff like that can help. But you emphasize the importance of structuring. Well, that's an interesting question. Can you use Chat GPT not to try to write the proof, but try to take a proof and structure it? That would be a nice thing for somebody to work on.
Whoever wrote that question, you should work on that right now.
All right, and this is the last question. So if you feel it's repetitive, we just about fit exactly into the hour.
Scenario when you have a proposition, you're thinking about if it's actually a theorem or not, and it's a sketch. Well, what that means is that you really need to before you try proving something, you should try to do everything you can to try to make sure it's true. Now, what I do is proving correctness of algorithms, and people I talk to, that's one of the things they do. I keep telling them, don't start writing the proof. Start modeling, don't start writing a proof of the algorithm. First, model check the algorithm. You test it. Do everything you can, because, like I say, it's much easier to prove something if it's true. Fortunately, that is the case with machine check proofs. It doesn't seem to be the case with mathematicians' proofs.
Okay,
Amazing.
Parsa, that's the questions?
And that's time, and that's perfect.
Yeah, so I just want to conclude. Yasher Koach, Dr. Lamport, for your extremely insightful Q&A question. Can I get everyone in the audience to give us a virtual round of applause for Dr. Leslie Lamport?
I wish
Come
I
on,
knew what
guys.
that
Don't
meant.
be shy. Let's go.
Oh, I suppose
Excellent.
they should put their hands up virtually.
Yeah, they're like
Take it.
virtual clapping.
Somebody will have
Okay.
to add that to Zoom and Teams.
Yep. So, Dr. Lamport, thank you so much for taking your extremely valuable time to educate us students in our various respective computer science departments. Dr. Lamport, I'll be following up with you shortly to inquire where we can send you your official Georgia Tech merch and various other speaker gifts, as we would like to extend our deep appreciation for your time and your willingness to speak with us today.
Well, thank you. It's been fun, and and
Yeah.
a bit enlightening. I really like that question about how to automatically structure, to get AI to structure unstructured proofs.
I think that's definitely a problem domain that's going to be worth exploring in the next decade or so, and I see some promise in it.
Whoever wrote that question, you have to. That's your you're dedicated to that question for the rest of your life.
Yes.
So, good luck. Okay, so on that note, thanks everyone for your attendance, and we just really appreciate everyone that came out for this speaker series initiative. And again, we really appreciate your willingness to speak with us, Dr. Lamport. And we will see everyone next week. We're going to have Dr. Noel Capone, who's a Columbia University Business School professor that's going to talk to us about marketing strategies and technology. So we have like a variety of speakers.
And if you have any final words before we end things off here for everybody who's still hanging around.
Well, been fun virtually talking to you. And have a good rest of your day.
Thank you so much.
Thank you so much.
Thank you, everyone.
Lamport. And thank you, everybody who attended.
Bye.
Bye.
Awesome.